Okay, welcome back. Let's now have a look at the solution to problem 1. So the first thing we need to understand, or remember of course, is that to work out the direction of the magnetic field acting on a conductor, we need to use our right hand slap rule. And just to remind you, the thumb and the fingers and the palm are all at right angles to each other, and the thumb is always pointed in the direction of the current, the fingers are always in the direction of the magnetic field, and the palm points in the direction of the magnetic force on the conductor. So let's use our right hand slap rule and then work out which direction the magnetic force is on the conductor itself, on the wire. So clearly our fingers need to point in the direction of the field, so we will draw in our fingers in, I think we'll use white. Oh my God, terrible fingers. Anyway, you get the point. They're the fingers. Our thumb is going in the direction of the current, which is from west to east, so it's going to be pointing in that direction. And so that's the current, that's the field, and so our force is straight up. So the magnetic force is directed upwards. That's the magnetic force. We know that, of course, the force of gravity on the cable is going to be down. So there's two forces acting on the wire. There's the magnetic force, which is up. There's that wire. And there's the force of gravity, which is down. So the net force, which direction the net force is going to be in, will be determined by which of these is larger. So to work out the weight force, that's pretty easy. Weight equals mg, so it's going to equal 50 times 10, so that's 500 newtons. So that is 500 newtons. To work out the force due to the magnetic field, we're going to use the formula F equals Bill, sine theta. Now, because the angle between the magnetic field and the conductor is 90 degrees, our theta is 90 degrees, and the sine of 90 is 1, so it just becomes F equals Bill. So let's work out that force, and it will be, force will equal the magnetic field, B, which is 50 microtesla, which is 50 times 10 to the minus 6 Tesla, micro means 10 to the minus 6, times I, which is the current, which is 50 amps, and L is the length of the conductor in the magnetic field. Now we said earlier that the entire conductor is in the field, so we're going to use the entire length of the conductor, so that's 100 meters. So if we have a look at this, it's going to be 5 times 5 is 25. Then we've got 1, 2, 4 zeros, so it's going to be 10 to the power of 4, then times 10 to the minus 6, don't forget that. So we can simplify that as 25 times 10 to the minus 2, which will be 0.25 newtons. Well, I think it's pretty safe to say that the force of gravity is much, much larger than the force due to the magnetic field. So we can see that this force here is 0.25 newtons in the upward direction. So the actual net force on the conductor is going to be in the downward direction to the value of 499.75 newtons. Okay.